Oh my, I'm not even on stage yet and you're already applauding. Don't do that. Okay, so the way I figure it is if I walk away from this presentation and you all say clo instead of closs, okay, then I've won. I've gotten done what I wanted to get done. So you may know that I do a lot with history of networking. I have a podcast called The History of Networking. And what I'm trying to do here is just talk a little bit how we got to the concept of a spine and leaf network. And by the way, a lot of this is lived history. So yes, I am that old. I may not look like it. So everybody probably recognizes this. The first one there with the lady plugging in a thing is actually a crossbar fabric or a crossbar switch. I used to work on one of these when I was back in the U.S. Air Force. We actually had one of these. And you know, essentially what happens here is you call the operator and the operator says, who do you want to talk to? And so they figure out which circuit needs to be made to make the connection between a send device and a receive device. Now these were replaced by mechanical crossbars, as you can see down here in the corner. This is probably in a building distribution frame, if you know what that is. I used to work on those too. A building distribution frame. And this is a mechanical version of that. Each of those relays actually does the makes for these kinds of circuits. Now I'm going to get into a little bit about unidirectional and how this works, but this is kind of where we started from. So if you look at a crossbar logically, what you have is you have every device is split up into, you didn't get to know you were getting a tutorial on crossbars today too, right? But that's okay. Every device is split up into a logical send and a logical receive. So if device 1 wants to talk to device 3, where the blue dot is, there's some scheduler, and that's the person in the previous slide, is the scheduler, will say, oh, 1 wants to talk to 3, so what I'm going to do is I'm going to make the connection where 1's send reaches 3's receive. Now it's important here that the circuit make is all I'm talking about. I'm not talking about the traffic itself. The traffic itself runs bidirectional once you do the make. But you have to make the circuit in some way. And that's done by a scheduler by connecting those two wires. So again, each device has a logical send and a logical receive. So even your telephone handset in those days, or even today, had a logical send and a logical receive. Now this is a Stoger switch. How many of you have worked on this before? Yeah, okay. So we had a frame at McGuire Air Force Base that was about 12,000 lines, and it was made up of the primary frame, the main frame on the base, was a Stoger frame. So we had a large number of Stoger switches. And the way this works is that, you remember the old dial-type telephone where you have the circular thing, you know, and the dial pad, and it's not even like a pad, so that is actually driving a stepper motor. And that stepper, there's actually 2 stepper motors in a Stoger switch. And the steppers, when you dial the first digit, it drives the armature down the wafers, and you can kind of see the wafers here. They're circular wafers. So it drives the armature down the wafers, and the second digit you dial drives the armature around the wafers using a stepper motor so that you can cover 2 digits in each one of these. Now the Stoger switch was designed by an undertaker, I'm not kidding, who was convinced that the lady running this in the small town where he lived was married to another undertaker in the town. And every time somebody would call and say, I need the undertaker because there's a dead body to be picked up, she would direct the traffic to her husband, who was his competitor. So he got together with his brother and said, we can't have this, I've got to automate this process. So he designed the Stoger switch. That's why it's called the Stoger, because it's almond-bound Stoger. This was invented in 1891. These were very, very common. And this was, again, just designed to take the operator out of the circuit make process. So once you make the circuit, you still end up with bidirectional traffic flow, but you're making the circuit from send to receive, logical send to logical receive. What's the #1 tool for troubleshooting a Stoger switch? Huh? Contact fluid. So you walk around with your bottle of contact fluid when somebody calls in a dirty circuit, and you spray the Stoger switch down with contact fluid in the hopes of making the circuit not quite so dirty. So this is, again, lived experience. This is a larger Stoger frame, and you can see in the very back there, you can see some what are those? It looks like there are some circuit conditioners sitting on the back wall there, and there might be some crossbar fabrics up there. What we would normally do in the old telco days is we would run the main frame off Stogers, and we would run the building frames off of mechanical crossbar switches. So you would have a BDF and you'd have trunks between them. Now the trunk lines are interesting because what happens is you couldn't run the trunk line, you couldn't power it, you couldn't get enough power to run the trunk line in mass. So you couldn't have a trunk line for every circuit that you might have. So on McGuire Air Force Base, we had a 12,000 line Stoger switch, and we had multiple BDFs that were crossbar, smaller crossbar frames, and we would have 200, maybe 100 pair that would be punched down on 66s to get you between the BDF and the mainframe on the network. I told you I'm old, okay? Much older than I look. Anyway, so the trunk lines are very, very difficult to drive electrically, so you'd have very few of them. Therefore, this is how you get into the whole concept of long distance before we had voice over IP. Now, this is the way a Stoger frame is wired. I'm getting somewhere with this. We're going to get to spine and leaf in just a minute. Trust me, we're going to get to the clo fabric and where it comes from in just a minute. All right. Each switch is one port. So if you think about the way I described the Stoger switch, there are 10 wafers and an armature that drives down the 10 wafers. And then each wafer is circular, and there are 10 connection points on that. So it's a 1 in, 100 out switch is what it is. I have 1 input and 100 out possible outputs. So what I would do is I would wire 3 stages of Stoger switches, which gives me 6 digits. And then if I want to do long distance, I add a Stoger switch to take me to a frame or to a trunk line. That gives me my 9-digit phone number. Okay, and I have 0 and 1, which is a precut in the frame. So this is how you get to a 6-digit phone number. Is you have 3 stages of Stoger switches, and each wafer output of the Stoger switch is actually wired to the core of another Stoger switch. So you get this kind of spine and leaf concept going in the layout of the Stoger frame. These were very, very painful to wire. They were all hand soldered. So you'd have 12,000 lines of Stoger, and you would hand wire all of this running. We went to wrap downs eventually, but most of the early stuff was done with soldering. So this is how you get a clo fabric. Now, Charlotte Clo in 1952 or 1953, you may have heard this bit of the history before, said these Stoger switches, they are very expensive to run. They suck up a lot of power. They're very hard to tune and maintain because of those pairs of armatures and that 1 in, 100 out. So he said, how can I replace the Stoger switch with something that is going to be more heat efficient, more power efficient, and actually make it where I can scale? The Stoger switches, as you can see as well, are extraordinarily large and heavy. They take up a lot of space. Whereas if you compare that with these crossbar fabric switches, they're a lot smaller and they take up a lot less power. So this guy, Charlotte Clo, he's trying to figure out, these crossbar fabrics are getting too expensive and too hard for me to manage. So what do I do to get rid of all this mess and make it smaller? So what he did was he took the Stoger switches and he replaced them with crossbars, hence the Clo fabric. And so all you're doing is you're using a fixed, originally they were 10 input, 10 output switches, and you replace all of your Stoger switches with these crossbars. Now, you always have 3 stages in a Clo fabric. Always. It's not 5, it's not 7, it's always 3. If you go to 5 or 7, it's called something else. Again, you know, my whole job here today is to get you to use the right words for the right things. All right, so multiple inputs, et cetera, et cetera. Now again, a Clo fabric is designed for telco. This is 1952, y'all, okay? This is probably before most of the people in this room were born, including me. This is a unidirectional fabric make situation, okay? I have logical send and logical receive on each one of these devices, and I actually do setup. I do a make across the fabric, and then I actually get the make, and once the make is made, then I can actually run traffic in both directions. So this is a unidirectional setup. It's non-blocking, has a very specific meaning of non-blocking. It's non-blocking because if the circuit is busy, I fail at the edge of the network. This is going to come into play when I talk about non-blocking versus non-contending, because packet switch networks are never truly non-blocking. We use the term, it's not really what it is. They're really non-contending. Anyway, so I have what I can consider to be edge admittance quality of service here. If I make it through the edge of the network, I have a circuit, I can make the circuit, I can transverse traffic. So it's non-blocking because I block at the edge. The network itself does not block traffic. Only it's dropped at the edge of the network. Now, when I switch this to packet switching, and I have bidirectional forwarding, this is what's called a folded flow. Now, we use folded to mean we flipped it over so all the spines are on the top and all the leaves are on the bottom. We draw it folded. Really, what folded means is it's bidirectional. Since packets can now be dropped in the network, it means it's non-contending rather than non-blocking. Unless you're going to set up edge admittance to ensure that you don't drop packets, it's truly a non-contending fabric rather than non-blocking. So some interesting concepts behind the idea of a fabric in the first place. Why is it a fabric rather than just a network? A fabric is a subset of network topologies. So first of all, it's regular and repeating. So if you look at A2, A1, B2, and B1, they are connected pretty much identically to B2, C2, C1, and C2. And those are all four connected pretty much identically to C2, D2, C1, and D1. Okay, so the connections are, it's a mini kind of modularization. Okay, I have like this micro modularization that allows me to pick up any part of the network and place it someplace else. So that's the first thing, it's regular and repeating. The second thing is it's non-planar. If you look at any of those connections where those connections cross. Now in the old days, I would draw this if I were doing it on a board, but in the old days when I was doing electronic circuits, I would take one circuit line, one run on my circuit board, and I would draw a second circuit and I would go, oh, they're not going to connect. So I would draw a little hump in it to draw over the other circuit. And when I draw the hump in it, what I'm doing is I'm breaking outside of the plane of the circuit board. Okay, this is why you have circuit boards with multiple layers, because I'm breaking outside the plane. So that's why it's called non-planar. I cannot draw a fabric, a clo fabric, or a spine and leaf of any kind, and make it planar. You have to have points where the two links overlap, and they don't connect. There's no cross links, so you don't have connections between A2 and B2. Because all of your traffic in this type of network is driven what's called east to west. Okay, I don't have any north to south traffic in a clo fabric. It's all east to west. And any north to south traffic that exists in my network design, I actually drive it east and west across a clo fabric. So I don't have cross links to facilitate north and south traffic flow. It's also scale out. The scale is only limited by the device port count. I think I have slides in here. All right. So there's this thing called a rearrangeable clo. We actually don't use these for the most part. Well, I say that, but I'll talk where we actually do use a Benet in one place. This was originally invented theoretically by Vaclav Benet. It was described by other people. This introduces the idea of planes. If you look in the middle, you'll notice there are two clo fabrics kind of in the middle, left to right. Okay, and those are planes, so you can build multiple planes. So this is the first kind of spine and leaf fabric that introduced planes. This is a Benet in packet switching terms. And if you ever build a three-stage spine and leaf, but you build it with chassis boxes in your spine, you're actually building a Benet. Because there's a fabric inside the chassis device that's connecting all the ports together. So it's actually a second layer or a second stage of fabric. So it's actually a 5-stage Benet is what you're actually building. Okay, this is when you put all the spines on the top. I think that's ugly, so I'm going to ignore that. There's this concept called a fat tree. This is a universal topology. Charles Learson in 1985, fat tree is a pretty new idea. Each stage has twice the bandwidth. What I mean when I say a universal topology is that you can take any topology and build that topology using tunnels on top of any other topology. So you can emulate a full mesh on top of a ring, or you can emulate a full mesh on top, or a ring on top of whatever you want to do. Mathematically, you can figure out how much efficiency you lose, how many additional hops and stretch you put into the topology by emulating one topology on top of another. That's called the efficiency of the topology. A universal topology is one that loses the least efficiency no matter what other topology you emulate on top of it. So now if you think about why do we use spine and leaf, even though we don't generally use true fat trees, spine and leaf comes close to a universal topology, even if it's not a fat tree. All right, this is what I call a butterfly. People don't like me calling this a butterfly. I don't know why. I don't know any other name for it, so I call it a butterfly. All right, this is a butterfly fabric. So if you look very carefully, you'll see I've color-coded the planes. So I'll show you a different picture in just a second, which is how you normally see it. This is split out. And by the way, I always draw my fabrics with the spine in the center. So you just have to adjust your thinking to that. My top of racks are all white. And then each of those sections, like you see the blue, orange, green, gray, and then the white below it, that's a pod. So this gives you a nice pod architecture that you can scale out very easily. And then you can backfill in those planes, what are called the fabrics, the fab routers, in the middle, piece by piece, to scale your fabric up. So this is typically what you see almost all hyperscalers using. This is what it looks like from the top. And this is what it looks like in 3D. Now, I know you probably can't grok that image, but this is what you'll probably see it drawn like all the time, okay? And you'll see those fabric switches down at the bottom, and then the spine switches. Those are your fabs. See, so it turns crossways to each other. Your fabrics are cross to your pods, essentially, is the way this works. And you can scale it out by increasing the number of devices in any given spine plane that you want to. This is how you normally see it drawn. This is a max size 8-port. Is that right? Are these 8? Yeah, these are 8 ports. So this is a max size fabric with 8-port devices, which you would never build because you would never use 8-port devices. But anyway. But you can see in this image, once I show you that other picture, how your planes kind of run counter to your pods. Your pods, so your pod runs top to bottom or bottom to top, and your planes run right to left. And so they kind of run cross to each other. Some people like to call this a crossbar, but it's really not a crossbar because it's not a crossbar. Let's talk about some scaling. If I'm going to talk just a straight clo fabric with nothing else, using 64 by 100 gig devices, I can use a 32 by 3 fabric, so 32 wide. So to scale a clo fabric, all I do is I take the number of ports on the device, I divide by 2, that's the width of my fabric. Closed fabrics are always 3 stages, so it's going to be 32 by 3 with a 64 port device. If it's going to be a 32 port device, it's going to be 16 by 3, okay? And I can build 81, so if I'm running, the way I've played my little math here is, I've said I'm running all 100 gig ports, and I'm using 4-to-1 opticals to give me 25 gig down to my servers. So, Kayer, I'll send you the slides, don't worry. He's taking pictures over here. Anyway, so I'm figuring that I will have 2048 by 100 gig facing out, and using 96 by 2 RU switches per fabric with 8192 by 25 gig facing out. So using 64 port devices, I can get up to 8192 by 25 gig port using just a 32 by 3 fabric. If I'm using 32, of course, you just divide it, like it's down by a quarter or whatever that is, right? And it's 48 by 1 RU boxes. So this is kind of what you get to with a straight clo fabric in terms of scaling. Now, of course, you can play with numbers, and this is all 1-to-1 oversubscription. I've not done any oversubscription in any of these numbers. Now, this is a butterfly. If I was running 4 fabrics like what I show here, that's the same scale as a full-out 62 by 100 or 64 by 100 using a straight 3-stage clo, but this is now a 5-stage fabric, right? Because I have my pods. Top of racks, I have my spine, I have my fabrics, I have my second spine, and then I have my top of racks again. If I was running that, I would get 8192 by 25 gig port facing out with 4 fabrics with a 32 by 100 device. The max size I can build with 32 by 100 in a butterfly is 16 fabrics. Why? Because 32 divided by 16, or divided by 2 is 16. So I can have 16 fabrics, gives me 32,768 by 25 gig facing out ports on that size fabric. Now, if I go to 64 by 100 devices, which are 2 RU, you can start seeing some of the numbers I can get. The max I can build is going to be 32 fabrics, which is 262,144 by 25 gig facing out ports in a 5-stage butterfly using 32 fabrics. So 32 of those green, you'd have to come up with 32 different colors to make it work, right? Because you got to have the colors. Wide, and each one of those is actually 32 wide because it's a 64 port device. Okay, so anything you do, you just take your port numbers and divide them in half and you can figure it out. The real trick is that if you want to know how big of a fabric you can build, again, take the max ports on the device, divide in half, that's the number of fabrics, that's the number of devices in the fabric, each one of those fabrics in a butterfly. Then you just count the number of ports you have in the spine, that's identical to the number of ports you have at the edge, at whatever speed you have with one-on-one, one-to-one over subscription. Okay, I think I'm at the beginning again. I didn't realize it would flip on me. So that is it. I just hope I convinced you to say clo instead of clos and write it with an uppercase C and lowercase LOS. It's the guy's name. And use the proper term for bene. I don't know what to call a butterfly other than to call it a butterfly. People fuss at me about that. So any questions on my little spiel about spine and leaf fabrics? Tony.
Tony Tauber, Comcast. Great presentation.
Thanks.
I think it's pronounced Benesh.
Oh, is it pronounced Benish?
Yeah.
See? Could be. I didn't research that one. I researched Clo. Anybody else want to call me out and tell me I'm wrong? Which is perfectly fine, by the way. I don't care. Oh, got somebody scooting to the microphone. It's a long way to the microphone. They need to make them closer. It's too big of a meeting room.
Hey, great talk, Alan Hanna and CrowdStrike. It's Stroger switch.
Oh! And I even worked on them. Thanks. So anybody else want to call me out and say I'm wrong?
Hi, Paul Schultz, Google. You said you would never build one of these out of an 8-port switch. We did in 2004.
Okay, well, in 2004, yes. Yes, you would in 2004.
Yeah, and
Today
the cabling was pretty crazy.
Yeah, right. Today, I don't know that I would build one out of it. Could you even buy an 8-port switch today, other than Linksys? I hope not. You could build yourself an 8-port butterfly fabric in your house out of 8-port Linksys switches. Get a lot of devices on it, I guess. All right. Well, thank you.